Hi everyone, welcome to Integral Calculus. Today we explore lesson 7.7, Approximate Integrals, part 1. Number 1, the idea. There are a few reasons why we need to approximate the integral. The first one is we have integrals with non-elementary antiderivatives, such as integral of 0 to 1 e to the x squared dx. There is no antiderivative of e to the x squared. Similarly, integral 0 to 1 root of x to the power 3 plus 1 dx, we don't know any elementary antiderivative of x to the 3 plus 1. We can solve this problem later on, but for now, it has to be the approximation that will get us to the answer, very close to the actual answer. Another reason why we use approximation is there are geometric shapes that we cannot figure out the area easily, such as the picture below, this one. And we also have a table of period data, real life data, in which we cannot use a function to model the data. So we have to actually plot the point and do the approximation of the area under the curve. Let's take a look at how we do the approximation of the integral. 2. Approximation using straight lines. There are 2 ways to use the straight line to approximate. The first way is use the midpoint rule. So that is for an integral from a to b of fx dx, that is the area under the curve. We use the midpoint, so we let a equal x sub 0 and b equal x sub n. The first midpoint is going to be the midpoint between x sub 0 and x sub 1. And we draw the line, get the corresponding rectangle. This rectangle has area, length and width, because we divide the line segment between A and B into n equal part. So the width is b minus a over n, and the length, well, it's going to be the output of the midpoint, half of x sub 0 plus x1. Yay! Similarly, we can get the next area between x1 and x2. We use the midpoint and we sketch the corresponding rectangle. The area of the rectangle is same width, b minus a over n. Length is f of half of x sub 1 plus x sub 2. Add up this area and we have a nice approximation of the area under the curve using the midpoint. Integral from a to b fx dx is approximately equal to the width. We can factor it out, b minus a over n, and then we add up the length, f of half a sub 0 plus a1 plus dot 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 plus the very last one, f half of an minus 1 plus a sub n. Yay! When we use the midpoint rule, there are errors in the approximation because some errors are above the curve and some is under the curve. We can compute the error using this formula. Error. Suppose the absolute value of the second derivative is less than or equal to a number k for all x in the interval a to b. Then the error of using the midpoint rule is less than or equal to k multiplied by b minus a to the power 3 over 24 n square. The second method of using straight line is call it the trapezoidal rule. So to calculate the trapezoidal rule, that is what we do. But we just have to create a trapezoid. X sub 0, here come x1. And we create a trapezoid. Yay! This area is half of the width multiplied by the sum of the two parallel length. B minus a over n fx sub 0 plus fx1. Similarly, for x sub 2, we can figure out the area between x sub 1 and x sub 2 by draw a straight line and get a trapezoid. So area is half of the width b minus a over n multiplied by the length fx1 plus fx sub 2. Yay! Add them up. And the integral from a to b fx dx is approximately half of b minus a over n multiplied to, well, f x sub 0 plus, we have 2 copy of x sub 1, 2f x sub 1 plus 2 copy of f x sub n minus 1 and plus f x sub n. Wow, it's pretty cool. When we use the trapezoidal rule, we also have an error that we have to consider. The error here is, suppose the absolute value of the second derivative is less than or equal to k for all x in the interval a to b. Then the error using the trapezoidal rule is less than or equal to k times b minus a to the power 3 over 12n squared. 3. Approximation using parabola. The method is called the Simpson Rule. Let's consider the function fx, same as the other two graphs up there. From a to b, So now, if we look at the graph, right, we see there's the point right here. And let A equal x sub 0. The distance from x sub 0 to the y-axis is h. So I'm going to call it x sub 0 negative h. In the middle is x sub 1, and right here is x sub 2, that is h. B is x sub n. So we all see that h is b minus a over n. The first point right here is negative h y sub 0. Second point, 0 y sub 1. The third point, h y sub 2. Now for these 3 points, well, we can fit them using a parabola. So of course there's a parabola that can go through these 3 points. Look at this parabola here. And the parabola here is gx equal to ax squared plus bx plus c. Now let's figure out the area under this parabola. Area integral from negative h to h, ax squared plus bx plus c, bx, that is ax to the 3 over 3 plus bx squared over 2 plus cx. Evaluate from negative h to h. Do the substitution. And we have a ah to the power 3 over 3 plus bh squared over 2 plus ch minus when we sub in the negative h, we have negative a h to the power 3 over 3 plus bh squared over 2 minus c h. Distribute the negative n. You see that bh squared over 2, they cancel each other out. Yay! What we have is 2 ah to the power 3 over 3 plus 2ch. I'm gonna do a common denominator here. So multiply by 3 over 3. And this gives us factor out the h over 3. Then we have 2ah squared plus c. Now, how do we rewrite this expression? Let's take a look at the y sub 0. Y sub 0 is g negative h. That is, well, according to this one, you see, y sub 0 is g of negative h. A h square minus bh plus c. Y sub 1 is g of 0. Right? So that's just c. Y sub 2 is gh, and it's ah square plus bh plus c. Oh, so to get the 2ah square plus 6c, right, we need to multiply this by 4, right? And then from here, we add them up to get y sub 0 plus 4y1 plus y sub 2 is 2ah square plus 6c. So we know exactly what it is. And now the equation become h over 3 multiplied by y sub 0 plus 4y1 plus y sub 2. Notice that the area only depends on the y coordinate of the 3 points, and we can shift the parabola to any sequence of 3 points. This means that the next area will start from y sub 2 and we end up with y sub 4. What this means is that the area under the curve using the parabola or the Simpson rule is approximately. So I'm gonna, the area is integral from a to b fx dx, so it's approximately equal to h over 3. H is b minus a over n, so that is 1 over 3 b minus a over n. In here we have y0 plus 4y1 plus y2. The next area y2, 4y3, and y4, so on, so forth. Add them all up and we have y0 plus 4y1 plus 2y2 plus 4y3 plus plus 2y n minus 2 plus 4y n minus 1 plus y sub n. Yay! And that is the approximation using Simpson rule. The approximation only works when n is even. So n has to be an even number. Even. For every approximation, we have error. And the error here is suppose the fourth derivative absolute value, f4 of x absolute value less than or equal k for all x in the interval a to b. Then the error using the Simpson rule is less than or equal to k times b minus a to the power 5 over 180 n to the power 4. Thank you for watching. I hope you found the content useful. Please like and subscribe to help the channel grow. I will see you in the next video.